Let us start lecture 21. In our last lecture, we tried to draw an eutectic phase diagram, and that time our condition was that binary system A and B, the constituents of that binary system, have the same crystal structure, and in the solid state, after forming the solution, they have the same crystal structure in case of solution, and we try to consider the situation when enthalpy of mixing for the liquid solution is negative or 0, and another case when enthalpy of mixing for solid solution is greater than 0. So, because solid solution enthalpy of mixing is greater than 0, so we have experience of phase separation. So, we tried to see, this is my eutectic phase diagram. This is my eutectic phase diagram, where this is liquid, this is alpha 1, this is alpha 2, and this is alpha 1 plus alpha 2, and this alpha 1 and alpha 2 both have the same crystal structure. And this is my eutectic composition, this is X0 X eutectic, and this temperature is T eutectic, that means eutectic temperature. This side is A and this side is B, pure side. This is T M A, this is T M B. Now, we drew free energy composition diagrams at 3 different temperatures. One temperature was chosen, this one, another temperature was chosen, this one, and the third temperature was the eutectic temperature. And we saw a situation, that means the equilibrium between different phases. So, first thing, if I try to see a free energy composition diagram for a system where the system is at temperature T eutectic. So, at T eutectic, both the pure states are in solid condition, but those are, if they are at solid condition, then the solid line would be, if I try to see, this is a reference value which is 0, this is g axis, this is x b, and the liquid would be, because in the pure side the liquid would be higher free energy than compared to the solid free energy, this is G2 solid. If I try to draw free energy of liquid, this is my free energy of liquid, this is G2 liquid, and now I have a common tangent. This are the compositions. So, this composition correspond to this composition corresponds to eutectic composition, and this one indicates the composition on the B rich side, and this temperature is basically T eutectic. Now, at higher than melting temperature, we had a free energy composition diagram. This is arbitrary 0 value. Here also, if the temperature is higher than T eutectic, that means the temperature I am considering this. So, that case also, on the pure side, solid free energy should be lower than the liquid free energy, because pure side already it has formed solid. So, it will be again the similar pattern. Liquid free energy line will be lower than the equilibrium free energy line, that means the common tangent between this point and this point, and the liquid free energy should be lower than that. So, that is what we have two phase common tangent. This is x solid in equilibrium with liquid, this is x liquid in equilibrium with solid. Now, here I have considered alpha. So, let me put it at alpha 1, this is alpha 1, and this composition would be x liquid alpha 2, and this is x alpha 2 liquid. It means that this is the composition of alpha 2 of solid solution in equilibrium with liquid. So, if I see that those four points, so this is the point which is nothing but x of alpha 1, this point is in equilibrium with alpha 1, and this composition is the liquid composition. This is the liquid composition again in equilibrium with alpha 2, and this is the composition which is this one in equilibrium with liquid. And we had another consideration which is the temperature, this one which is below T eutectic. So, that time again a solid would have a lower free energy, and if I take this is as a reference value, again this would be having a plot like this. So, this point and this point would go and meet 0 point, but the liquid line would be above this common tangent between two solid phases. So, this is x alpha 1 in equilibrium with alpha 2, this is x alpha 2 in equilibrium with alpha 1, but the liquid line either it could be here or it could be here, but it will be above that these two, this common tangent line. So, we cannot have liquid phase as a stable phase. Okay. So, depending on the temperature, if that temperature is such that the liquid line goes up to a great extent, and it can be temperature could be such that the liquid line could be little lower than that, than this, but it should be above this common tangent line, this common tangent line. So, that case we have two concentrations which are in equilibrium. This is nothing but this composition, and this composition is nothing but these compositions. So, we had an eutectic phase diagram where our conditions was where del H mix of liquid, either it could be 0, considered as 0, or it could be considered as less than 0, or del H mix solid, another case is greater than 0. But since we have a continuous solid solution line, here crystal structure of A and B same crystal structures. Same crystal structure, and the solution also has the same crystal structure. Solution or the alloy has got the same crystal structure. So, this is one situation we have talked about. Now, we have to get into another situation where my conditions are del H mix of liquid is very low and highly negative. That means, what does it mean? If I try to see the construction of del H mix, this is my minus T del S mix, and since del H mix of liquid is very low, that means very negative, very much negative. So, it might have very steep, this is del H mix of liquid. So, now del Gmix would be just addition of these two, and this would have a very deep del Gmix. And accordingly, if I try to see what happens to the del G2, that means this is G1, I know this is pure A, GA0, GB0. So, if I try to see G2 for that particular liquid phase, then G2 would be having very steep situation. This is the G2. Now, if ΔHmix of liquid is negative, but not highly negative, the only difference would be in the ΔHmix thing. So, if I try to plot ΔHmix of liquid a lower negative, so this would be this one, minus T del S mix would not change. So, del G mix would have a lesser dip, and then G2 also would have lesser dip. So, this is G2 when this condition is del H mix of liquid is greater than 0, and in this case it is del H mix of liquid less than 0. So, now this situation when it arises, then we have a much deeper G2, and another situation could be del H mix of solid is equal to 0. So, automatically according to this explanation, G2 of solid solution would have less steeper G2. So, now let us say I consider a situation T which is greater than Tm of A, greater than Tm of B. That means the melting point of A is higher than melting point of B, means when I cool down from a temperature which is beyond the melting point of A, and as we cool down, the first solid phase that would appear is basically the pure A. Now, if the temperature is greater than Tma and greater than Tmb, so everything would be liquid for the entire composition range. So, our composition free energy composition plot, if I try to plot, this is my arbitrary 0 value, this is the reference value, and then solid, liquid, I can say that this is pure liquid A and pure liquid B. So, this is my liquid line G2, which is G2 liquid, which is very steep, and solid line should have appeared higher than this, because at that temperature I cannot have any solid. So, solid line would be like this. This is G2 of solid. Now, this is G and this is X B. So, now second situation, T is Tm A, Tm B, then the temperature is such that the pure A side I would always get A phase, pure A solid, and on the B side I must get pure B in the form of liquid. So, if I try to draw this free energy composition diagram, this is arbitrary 0 reference. On the A rich side or A side, pure A should be solid. If I consider to be 0, then the liquid should be above that, because the temperature is such that this is lower than the temperature melting point of A. So, the A should appear in the pure condition. And whereas on the B rich side, since the temperature is beyond the melting point, is greater than the melting point of B, so there the liquid would be the stable condition. So, the liquid line I can draw it like this, whereas the solid line on the right side, this is pure B side, B rich side, solid must have higher free energy, because then only B can appear as a liquid. So, this is G2 liquid, this is my situation, this is G2 solid. So, now I have a common tangent here. So, this is composition X alpha with liquid in equilibrium with liquid, and this is X liquid in equilibrium with alpha. Now, third condition we can have, which is T less than Tm B less than Tm A. So, that means on both pure A and pure B side, I must get solid, pure solid of both the components, both the elements. So, that time if I arbitrarily draw that particular situation, this is 0, it is a reference point. So, now this is, let us say I start with pure solid, because I must get pure solid when T is less than Tm A, this is A rich and this is B rich. So, the solid will start here, and similarly on the right side also I must get solid B, because the temperature is less than TMB. So, the B also would solidify in the pure condition. So, now solid line is like this. So, on the pure side liquid lines are like this. So, G2 this is G2 solid. Since the liquid has got a very steep G2 line, so this is G2 liquid and this is G2 solid. So, if I see the equilibrium condition, I have this equilibrium, at the same time I can have one more equilibrium like this. This composition is X alpha in equilibrium with liquid, this is X if I consider to be alpha 1, because on the both the sides I am getting alpha phase, because the free energy line is continuous and they have the same crystal structure. So, this is, but in order to distinguish between these two solids, because these two solids have different A content and different B content, one is A rich, another one is B rich. So, that time I can put it as X alpha 2 in equilibrium with liquid, and this is X liquid in equilibrium with alpha 2, and this is X liquid in equilibrium with alpha 1. And now, if we go down further, the temperature is such which is still TMB is less than TMA, I can have a situation, the free energy situation, free energy line. This is my solid line, this is 0 arbitrary reference. Now, the liquid line can just touch at this point. So, now if I put all those compositions whatever we have drawn till now, 4 temperatures, this is, let us go back to this is temperature 1, this is temperature 2, this is temperature 3 and this is temperature 4. If I try to draw their, this is X, B, this is A, this is B, pure side. Now, I would get a, if I try to plot all those temperatures with these temperatures, I just draw 4 temperatures, and here I get these 2 points, and then I get these 2 points. First one is I do not get any points there, actually I do not get any points there, because every time it is a liquid stable. So, here I get 2 and I do not get anything, but here I get this and this 4 points, and finally I get this. So, if I try to do it complete, we would get a plot like this. So, this is liquid, this is temperature, this is alpha 1 plus liquid, this region is alpha 2 plus liquid, and this is solid, which is alpha. So, I am getting a situation when I am having, you see, because the liquid free energy line is G2 line is very steep, that is what I could get the liquid stability at a very low temperature. Now, this situation becomes opposite if I consider ΔHmix of solid to be less than 0 and ΔHmix of liquid is either 0 or less than 0. So, that situation I would request you to just solve this. You can get help from the thermodynamics book of Gaskell. So, there the phase diagram would look like so. This will be my liquid, this will be my solid, this is alpha 1 plus liquid, this is alpha 2 plus liquid, this is xb, this is temperature. And that time I am getting a point which has the maximum, that solid has the maximum melting point, it is called congruent phase. Now, in case of a system where now the situation would be reverse if we consider these conditions. The solid ΔHmix is very negative, highly negative, whereas ΔHmix of liquid is either 0 or slightly negative. That time I would have much steeper free energy line for solid solution, but less steeper free energy line for the liquid solution. So, one such situation would be, let us say the temperature is basically higher than TMA and higher than TMB. That time I would have a free energy plot. If I consider this is my arbitrary 0 value, then for the entire composition range the solution would be liquid. This would be G2 of liquid, but since ΔHmix of solid is highly negative, so G2, which is G1 plus delta Gmix for solid, which will be very steep, I can have G2 of solid like this. Now, if temperature is such that it is greater than TMA and greater than TMB, this is T1, this is T2 still, but T2 is less than T1, that time this liquid line would move off and the solid line would move down. So, then I can have a situation like this. This is arbitrary 0, because both the sides pure A and pure B both are liquid, because the temperature is such that pure metals should be in the liquid condition. So, this is my liquid line, but the solid situation is such that the solid is just touching the liquid line, this point. So, at this point this composition of solid would appear in equilibrium with the liquid. Now, if I decrease this temperature further, T3 is less than T2, but T3 is greater than TMA, greater than TMB, that time I could have a situation like this. On the same diagram, situation could be like this. So, that time this is G2 of solid, and then I would have a two phase, two equilibrium common tangent. So, this would be my x alpha 1 in equilibrium with liquid, this is x liquid in equilibrium with, let us say, on the other side B rich side I consider alpha 2. So, this is alpha 2, this would be my x liquid alpha 1, this composition would be x alpha 1 liquid. And finally, I would get a situation, T 4 less than T 3, but T 4 is less than T m A less than T m B less than T m A. That case I would have a situation like this. This I can do it here. So, solid line would be steep and the liquid line would go like this. So, that case everything would be solid and my phase diagram would look like because T B side, this is A side, this is T m A, this is T m B. So, I would get a phase diagram like this, and this point is called congruent melting phase. So, let us stop here. We will continue our discussion in our next lecture. Thank you.